So, we just saw that the two equations which are very crucial to our structure determination are these, the structure factor expression and the electron density expression. Now, we will see what is the relation that comes in the geometry point of view, because the relation that comes from the electron density we now know, because the more the electron density, the more is the scattering. Suppose you have a very big atom and a small atom, the contribution from the big atom is more to the scattering compared to that of a small atom. So, X-rays therefore, now if one used, whenever we use them, we will have the intensities depending upon the strength of the electron density that is associated with the unit cell. Now, let us see what happens in terms of the geometries. Let us look at this figure. This figure is essentially showing this, that we have the incoming incident radiation. The unit vector is associated with this is S naught. We now normalize it with respect to lambda. So, it becomes independent of lambda. So, we can use any lambda. Remember that we are talking about atom sizes of the order of 1 angstroms. So, the wavelength can be anywhere between 0.4 to 2.5 angstroms. If we use that wavelength, we will be in a position to see the details associated with atoms and molecules and so on. So, therefore, we prefer to use X-rays in that range, about 0.5 angstroms to 2.5 angstroms is the range of X-rays we like to use. It is recommended that since the lambda is coming up as a normalization factor, it is recommended that we use a single wavelength. So, at this particular stage, I can introduce the way in which we generate X-rays. There is no slide or a diagram for that, because I thought it is probably not necessary. Instead, I will just give a narration, and that narration should be sufficient for our understanding of how we generate X-rays. You have all seen an X-ray tube, I suppose, and you have used, in fact, you have gone to, whenever you broke a hand or a leg, which most of you do, you go to a doctor and the doctor puts you through the X-rays. So, X-rays are generated in a vacuum tube, and these X-rays are generated in such a way that they come up from what is known as thermionic emission. That is, you take an element, a filament in fact, a tungsten filament, and that tungsten filament is heated with a certain small current. As the tungsten filament is heated, that is just like the light source we have. In the olden days, we had those incandescent lamps, which still some people use, but now we have replaced everything by LEDs. But this incandescent lamp used to have a filament, and when once you put on the switch, when the power goes in, the power is actually heating the element. The heated element now generates luminescence, and that is how you get the light. So, the light becomes now on, and as a consequence the filament glows, and filament glows because we have heated the element. So, the same heating we do, and now we have the tube, there is a vacuum tube which encloses the filament. Now, what really happens is, in this case of the filament heated, there is a certain region around that where we generate electrons. So, electrons get emitted. There is of course the usual heat, the Joule heat will be there. So, that is why if you put the light for about half an hour, the incandescent light, and go and touch it, your hand will burn. The reason is we have generated a lot of Joule heat. Apart from that, we have also used the concept of luminescence which occurred in the tungsten filament. Now, the process is now essentially generating electrons. So, these generated electrons now are put in a large electric field. So, we put what is known as a cathode, and this becomes now the anode. So, the cathode is now made up of an element. Okay. So, that particular element, maybe I will have to write some picture for that. So, instead what I will do is I will explain and tell you now in very simple terms that the electrons now get accelerated when we apply a very large field, and this field could be 30 to 40 kilovolts. That is the X-ray generator you will see. So, in the case of a typical medical X-ray, it is about 60 to 80 kilovolts of power, which now accelerates these electrons. There is also a certain current which is involved in it. We want the electrons to be generated faster rate, then we increase the current. In a typical laboratory experiment where we expose the crystals, that current is in milliamps. On the other hand, in a medical X-ray, the current is in amperes. So, it is about 60 amps. So, 60 amps and something like 60 to 80 kilovolts is what is applied in a medical X-ray situation. In when we want to expose the crystals, as you know, it is very, very small. The size of the crystal one uses it is about 0.3 millimeter cube. It is a very small crystal, and therefore, the power is not very high, it is not required. In fact, we can calculate the power. So, if we multiply 40 by 20, it is about 800, right. So, this is 800 watts. So, the power that is generated will be 800 watts. So, depending on 800 to 1200 watts is the power which we use in the case of when we expose the crystals to X-rays. On the other hand, in the medical X-ray, it will be now 60 times 80 or something. So, that is for 4800 watts, a very almost half a kilowatt. So, the X-rays now what happens is that these electrons now hit the cathode, which is an element. Now, this element has a certain characteristic X-ray. Maybe we will discuss that in a later class when we actually see the experimental setup. When we actually see how we set up the experiment to measure the diffraction, how do we use the detector, how do we generate X-rays, at that time we will consider that. But at this moment, these X-rays are accelerated to the cathode. The cathode is a particular element. Now, this element has some what we call as characteristic behavior. Depending upon where the K shell electrons are there with respect to this element, we get the intensity going up in X-rays. Otherwise, generally we get X-rays, normal X-ray, which is known as the white radiation. Like any other radiation you get a white radiation. Along with that white radiation, there is a characteristic radiation corresponding to the elimination of the K alpha, the elimination of the K shell electrons. When the K shell electron goes out, L shell electrons drop in, and therefore, we generate the X-rays. And those X-rays in case of medical X-rays are very strong. So, they pass through our body, there is no harm, but the X-rays which we use in the laboratory is so low in the power that we should not get ourselves exposed to X-rays. Anyway, let us say that we have generated X-rays now for our discussion. We will go to the experimental detail later on. So, we have the generated X-rays. So, this is the X-rays which are generated with a certain wavelength lambda. So, all this discussion came up because since I was using this lambda as a normalization factor, it is better that we in most of these experiments we try to get the lambda to be a single value. In earlier experiments which Laue and others did, which we are going to discuss now, they used white radiation. However, it is now recommended that we use what we call as the monochromatic X-rays. So, there is a single wavelength X-ray. So, the incoming incident beam is normalized with respect to that. So, this is the way in which it comes and falls on this electron density rho of r d of r, let us say it is up here. So, if there was no electron density, this would pass through, and therefore, this is now called the incident direction. S naught by lambda is known in this particular direction, it goes out into the system. In fact, depending upon the amount of electron density is present, since the energy that is associated with the incoming radiation is so large, most of the radiation will go through, except a little bit which now will go in the direction S by lambda because of the presence of the electron density. It depends upon how much of electron density is there. So, the amount of electron density decides how much of scattering intensity should come. So, this goes in this particular direction. Now, you see that if you calculate this angle, if you call this angle as 2 of theta, r now the vector r, which is S minus S naught by lambda, is the bisector of these two. So, there is S naught by lambda, S by lambda, this is the bisector. The vector r therefore is the bisector of S naught by lambda S by lambda. You can calculate what should be the value of r. A little bit of trigonometry you have to do yourself. So, I will leave the choice to you how to get to this expression. So, we get the modulus of the vector r as equal to 2 times sin theta divided by lambda. So, we therefore get the actual value of r depends upon now this so called scattering angle. The more the scattering angle, you see that the value of r, it depends upon the value of lambda. So, for a given lambda, the value of the scattering vector depends upon the value of theta. That means the direction in which it goes, the scattering direction in which it goes is not really indicative in this expression, which is only giving us the modulus of 2 sin theta by lambda. So, the direction in which it goes is following the S naught by lambda S by lambda, because that is the bisector of that. So, depending upon different values of 2 theta, this vector S by lambda can go anywhere between this to that. This can go from 0 to nearly 180 degrees. Now, how does S by lambda vary with respect to S naught by lambda? We can consider that detail by considering the possibility of having atoms put here, which we will discuss later. So, at this moment the modulus of r is equal to 2 sin theta by lambda. What you notice immediately is therefore, this quantity r, as we have been telling already, is inversely proportional to length, and therefore, this scattering vectors represent the vectors in reciprocal space. So, obviously, we have to now define a reciprocal space, which we will do in a little while from now. So, the essentially the idea is now to see that we can get the value of the magnitude of r. The phase angle anyway has to be determined, and therefore, we still have the phase determination remaining, but we can get the magnitude of r. Now, we will go into the realistic situation. Until now, we generally discuss scattering. We generally discuss scattering with respect to some electron density, which is lying in some space, rho of r d of r. Now, we will say that the electron density is associated with an atom, and more so we will make this atom a point atom. That means, suppose you consider a carbon atom, there are 6 electrons associated with the carbon, and of course, there is a nucleus, core and valence electrons and so on. Now, the whole thing we will condense it as though it has 6 electrons and say it is belonging to a point x y z. Then what happens is that any scattering that will occur, if we go back here, any scattering that will occur now will become independent of 2 theta, because this is now a simple point. If you now have a certain volume associated with this particular point, like here, small elemental volume we said, then we will have the scattering angle changing. Otherwise, if it is a point atom, you will just see the point atom and the scattering will go. So, it is independent of theta. So, this is a very serious approximation, but it will allow us to imagine a situation where we can calculate what is the quantity of what is the total information we can get from this. In this particular case, you see that we define now because of the fact that there is a scattering from a point atom, the point atom has all the electrons in it. So, therefore, if we now calculate this quantity called delta r, which is referred to as a delta function, which is written here, this delta function will be equal to 0 everywhere else, because atom is only at one point, a single point atom we have taken. The atom is at one point, and let us say that atom is located at r equals 0. So, if the atom is located at r is equal to 0, the expression up here, which we have written here, rho of r exponential blah blah, there is no dependence on the phase. So, it will be rho of r d of r. Okay. So, that will be integral rho of r d of r. So, what happens therefore is it becomes integral rho of r will be now written as delta of r d of r. This delta will be the total number of electrons. The total number of electrons present in this quantity integral delta r dr therefore is equal to c. C is a number which represents the total number of electrons. In case of carbon it will be 6, nitrogen it will be 7 and so on. So, this allows us to identify the atom as a single atom, single point atom, and then through the delta function. So, it has certain special properties that it is equal to the integration of delta r dr is equal to C at r equals 0, but everywhere else around the surroundings it is not actually a measurable quantity, it is equal to 0. Now what happens if there is an atom which is situated not at r equals 0, but away from r equals 0. So we now see that f of r can be written as integral delta r minus r prime. Now the phase factor comes in. How does it come in? It comes in because of the fact now the atom is not the point atom is not at the origin, it is removed by a quantity r prime. It is located at a distance r prime from the origin, and therefore we get this expression away from the origin by r prime distance. Then we have the phase factor coming in, and the delta function is at r prime from the origin, and then we will get this expression C, which is still the total number of electrons multiplied by the phase factor, which is exponential 2 pi I r dot r prime. So this therefore now gives us the expression for the structure factor. So if we consider a delta function which is at the origin, we get this expression. Delta function is a special case of f of r essentially, and therefore we now define f of r in the following fashion. So this happens if we have a point atom. Now suppose we have a large number of point atoms, which is essentially the crystal. In a crystal we have, let us say, 100 atoms. Let us consider all and each and every atom as a point atom. If we consider each and every atom as a point atom, they are located at r1, r2, r3 from the origin. So we sit at an origin, consider r1, r2, r3, r4, etc., the positions of the atoms. Then now corresponding to each one of these points we have to add it up. The total f of r therefore will be a summation, and this summation will be over all the r1, r2, ri. So therefore it represents C of I. So C of I therefore is the total count of the electron density. So if there are let us say C10 N2O5 H13, that kind of a molecule, and that there are 4 molecules in the unit cell, then C of I is the total number of electrons of the entire unit cell, and therefore we see that the summation is over the entire unit cell, but then the summation is over only the atom positions, because these are point atoms, and this summation will now give us the total number of electrons inside the crystal, and every one of them now has a phase factor depending upon where they are sitting. If they are sitting at r1, there is a phase factor, r2 there is a phase factor, r3 there is a phase factor, and therefore this now represents the structure factor for a collection of point atoms. So what we have done here is we have considered all the atoms to have only all the electrons and everything associated with the atom to be with a point, and this approximation is a very valid approximation from the point of view of calculating the structure factors. In fact, this is what we are going to use when we determine the structure by what are known as direct methods. So we will assume that, of course, this is an impossible situation. Atoms cannot be associated with one point. They have their own diameter in which they distribute the nucleus and the electron density around it and so on. For practical purposes, to get the evaluation of the structure factor, this therefore is a good and convenient method. So we say that there are a collection of point atoms. But what is the reality? The reality is the following. The reality is that there is a scattering coming from a periodic array. So when the scattering comes from a periodic array, we have a 3-dimensional lattice. We have the A axis, we have the B axis, we have the C axis. Suppose we now consider the atoms to be associated with lattice points. It is not necessary, but let us say each atom is now associated with a lattice point. Then we can generate this diagram. Now if we may generate this diagram, then we have to be able to calculate what is happening with respect to the scattering. So any vector in this unit cell, let us say we start from the origin, and let us say take this lattice point, where we say we have an atom in that lattice point. Because of the periodicity, it repeats itself. So from this point to that point, let us call this vector as r, the little vector r. The little vector r is in real space. This is actually the position vector, the position vector corresponding to the atom, let us say. So, this now is r, which is now represented by n1, n2, n3, 3 integers in the representing the 3 directions, the a direction, the b direction and the c direction. So, let us say if it is one unit cell, you have the a, b and c values coming up here. So, these are therefore the integral values or rational values more appropriately. So, any vector r therefore can be expressed in terms of these rational numbers or integral values n1 a1 plus n2 a2 plus n3 a3. So, we have therefore a lattice of points. Instead of point atoms being randomly distributed as we discussed before, the point now atoms are now associated with a lattice point. When we do that, we get the vector r to be n1 a1 plus n2 a2 plus n3 a3. The volume of the unit cell is given by a1 dot a2 cross a3. This provides the volume of the unit cell. At this stage, we now define a set of vectors b1, b2, b3 with very special properties. The properties are that if we take aj and take the dot product with bj, that is equal to 1, and aj is equal to bk equals 0 whenever j is not equal to k. So, that means when we have a1 dot b1, the value is equal to 1, a1 dot b2, the value goes to 0. Now, such set of vectors when we define using this expression, these vectors are supposed to be reciprocal of a1, a2, a3. Now, it becomes obvious to you why we are doing this. We are doing this in order to get the representation of capital R, which is our scattering vector, and we also know it has dimensions of reciprocal length. So, we are now trying to get how to express capital R given the little r in a 3-dimensional lattice. So, if when we have a periodic array, we consider the little r and we now want to define the capital R. So, when we do this operation, we can show that b1 will be equal to a2 cross a3 divided by a1 dot a2 cross a3. a1 dot a2 cross a3 by definition is volume. So, this now becomes a2 cross a3 divided by the volume. Similarly, b2 and b3. So, when we have these 3 vectors b1, b2, b3 following these vector expressions a2 cross a3 by v, a3 cross a1 by v and a1 cross a2 by v, defining the values of b1, b2, b3, then these set of vectors b1, b2, b3 will be able to quantify or will be able to represent the so called scattering vector r, because it defines now a lattice of vectors b1, b2, b3 just like this lattice. Suppose we now sit at an origin and now these are b1, b2, b3, we can define the values of b1, b2, b3. I am not telling a1, a2, a3 is equal to b1, b2, b3. b1, b2, b3 is inverse of b1, b2, b3 or inverse of a1, a2, a3 or the reciprocals of a1, a2, a3. So, if there are 3 vectors a1, a2, a3, the reciprocal vectors, that is 1 over a1, 1 over a2, 1 over a3 will be b1, b2, b3. And therefore, these b1, b2, b3 in principle should describe our vector r, which is s minus s naught by lambda. So, we therefore define what is known as a reciprocal lattice, which is built up of the 3 vectors b1, b2, b3. So, a1, a2, a3 are the real space vectors, b1, b2, b3 are the reciprocal space vectors. So, what we have done so far in this part of the discussion is to consider the atoms to be point atoms, and then we have considered the collection of point atoms, and then we have distributed this collection of point atoms to various lattice points in real space. And then we have defined the quantities which define now the reciprocal space, such that b1, b2, b3 are reciprocal vectors of a1, a2, a3. This will allow us to describe the little r, which is in direct space, and the capital R, which is in the reciprocal space. So, little r and capital R have dimensions of reciprocal length with respect to each other. R is the position vector in real space, capital R in principle is the position vector in the reciprocal space. So, if we have this knowledge, we will see what happens when we have a realistic crystal. Okay. Now, let us go further. this is what was done by Laue. That is why I put his picture here, which you already saw in the earlier class, because this is his contribution. Now what is it that is going to happen if we have a crystal, we have a lattice, we have A1, A2, A3 defining the vector R, and B1, B2, B3 defining the reciprocal lattice vector. So just like we described the little r n1, n2, n3 as n1, a1 plus n2, a2 plus n3, a3, where n1, n2, n3 are integers. Now we can describe the vector r in terms of h1, h2, h3. These are again 3 integers which will define h1 b1 plus h2 b2 plus h3 b3. So effectively from the real space you have gone on to a reciprocal space where you are able to express vectors in the reciprocal space. Now what we will do? We will do a small mathematical operation, that is to take the dot product of r dot r. Now you might worry why we are doing this r dot r dot product. We need this r dot r dot product because you see here you have in this expression r dot r. The calculation of the structure factor will be accomplished if we get this quantity r dot r. Okay, so we need to have this dot product between the real space vector and the reciprocal lattice vector. What happens when we do this is that r dot r will become h1 n1 h2 n2 plus h3 n3. n1 n2 n3 are integers, h1 h2 h3 are integers. So sum of 3 sets of integers will be an integer. So this will be an integral number. So the structure factor f of r, which can be now expressed, see now we will take the total electrons in the unit cell outside, total number of electrons, which is equal to the total count of the number of electrons associated with all the atoms in the structure. Okay, total count is C. Then sum it over n1, n2, n3, sum over all values of n1, n2, n3. We then write exponential 2 pi I r dot r. So this exponential 2 pi I r dot r now is the expression which will now allow us to determine the phase. This is the amplitude and this is the phase. You notice that the amplitude is now directly proportional to the total number of electrons. So that way we are in a very comfortable position. So we now substitute r dot r at this expression. So when we do this r dot r substitution, we will get exponential 2 pi I h1 n1 plus h2 n2 plus h3 n3, and this now represents every time a point in 3-dimensional space, and that 3-dimensional space is the reciprocal space, and therefore we get C times n. C is the total number of electrons, n is the total number of reciprocal lattice points, and therefore we get f of r is equal to Cn. Now what is happening here? If in terms of light, what is happening? So the incoming radiation is X-ray. So the X-rays now come and fall on the crystal. The crystal now acts as a periodic array, and because it acts as a periodic array, it generates the vector, every position vector little r generates the capital vector R, and therefore the product r dot r will be an integer value. So whenever the product r dot r is an integer value, you get light coming out. Whenever the capital R dot r is not an integer value, we will not get the light coming out. So what was continuous scattering? We talked about scattering occurring from an object. It scatters in all possible directions. Now these directions get in sometimes in a very loose term quantized. So these therefore now will occur in such a way that these atoms therefore will now become these points will now become organized, and they get organized in such a way that they have to satisfy this expression C exponential 2 pi I h1 n1 plus h2 n2 plus h3 n3, this now being an integer, and therefore only when these integral values are there you will get the light out, and whenever the integral values are not there you will not get the light, and this process is the so called process of diffraction. And this has been done by some experiments in your college days, which you might recollect. You would have done it with light. You would have done the light diffraction experiment and you were given a diffraction grating. So, this is essentially a glass piece where there were grating marks, they were marked with equal distances. This is essentially like the discussion we had on the two slit experiment. So, as we put more and more slits, it is equivalent of putting more and more gratings, and therefore, the moment you put gratings, the light which is coming in will now go through the grating, and the diffraction grating will give the specific directions in which light can pass through, and therefore, you get a diffraction data. This is essentially coming because of the lattice, because of the fact that we have a 3-dimensional unit cell which now repeats itself in all 3 directions, we get this information. So, it can happen only in crystals or crystalline materials. So, therefore, we get the diffraction, and this is what was discovered by von Laue, for which he was given the Nobel Prize. So, what did he do? How did he explain this? He explained it in this fashion. If you take R, R is now S minus S naught by lambda, we know this. This is the scattering vector. This is the direction of the scattering vector, its magnitude is 2 sin theta by lambda, we have just calculated that. Now, this now becomes vector H, and this vector H will not be all over the place, it is not a continuous function now, it will happen only if this value is satisfied, when it is H1 B1 plus H2 B2 plus H3 B3, H1, H2, H3 being integers. That means, these 3 conditions which are written down here, S minus S naught lambda is, in fact, you can write it as capital H, capital H times the vector A1, this is your unit cell dimension A. So, capital H dot A1 is equal to H1, capital H dot A2 is equal to H2, capital H dot A3 is equal to H3. You can replace H1, H2, H3 by HKL, which is normally used in many textbooks which you read, and these are the so called Miller indices. A1, A2, A3 you can replace by ABC. Therefore, this is the expression which Laue derived. So, the capital H, H1, H2, H3 represents what we call as a reciprocal lattice vector. The dimensions of the reciprocal lattice vector is proportional to 2 sin theta by lambda, and therefore, the diffraction will occur only when these Laue conditions are satisfied. So, that means when you send in the X-ray beam onto the crystal, only when all these conditions are simultaneously satisfied, then only you will get the diffraction. That means, when you have a 3-dimensional crystal, the diffraction will occur only in certain given directions, and those directions now will generate a point, and therefore, we get a reciprocal lattice point. How does it generate a point is still a question which we will answer as we go along.